Alright, good afternoon. Let's continue on the lecture from last week. Alright, so this is what we did last week. We were talking about open loop pulse transfer function, and one example we started basically given an actual part of the open loop. Okay, so you have an analog, a digital filter, digital analog, and plant. The equivalent math model, okay, so basically for this actual system can be simplified with a impulse sampler, the digital controller, the zero order hold representing a DA, and also the plant here. Okay, so let's plug in an actual basically example here, actual controller and an actual plant, and then we can look at the responsive system. In this case here, let's say if this is a controller, suppose that this controller is represented with this difference equation. So that's the difference equation right here, right? The input is E and output is M. So we can derive for the digital controller here. And here is your difference equation. So you can take basically Z transform, okay, of both sides. If you take Z transform both sides, and we get basically M of Z equal to 2 times E of Z minus, here's one delay, so Z times Z to power -1 and E of Z like this. So this is a difference equation, and that's the it's Z transform both sides, right? So then you can get the ratio between the output and the input, and the ratio of the output and input basically is the difference. It's a digital controller or digital filter D of Z. So that gives us 2Z minus 1 over Z. So that's the digital controller here, okay, based on this difference equation. And then you have this plant here. Okay. Now suppose that we're trying to simulate the response of the system, and we're going to look at the simulation in digital domain here. Okay. So which means I'm going to basically convert everything into the pulse transfer function. So this is G of S here. Okay. So we're going to basically transform that into G of Z, so obtain its G of Z. Essentially, you're gonna take the Z transform of that to get this G of Z here, and this G of S is a multiplication of the zero order hold and the plant at here. So zero order hold has a transfer function of 1 minus this. That's the zero order hold transfer function. And the plant has a, let's just leave the plant at here. The plant also has a transfer function which is given in the question here with 1 over S plus 1. So this is 1 over S plus 1 here. Now if you recall that in previous lecture, whenever you have a zero order hold and a continuous Laplace transfer function representing a plant, and if you wanted to take the Z transform of that, and this is basically the formula is 1 minus Z to the power -1 and Z and then GP of S over S, right? So that's the from here to here. Okay, consider that as a formula now. Okay, so whenever you have a zero order hold in front of this plant, okay, and this is your resulted Z transform. So plugging this plant here, plugging the plant S function, which is 1 over S times S plus 1. Right, so the plant is 1 over S plus 1, and then divided by another S, which is the integrator here. So you get this one here. Okay. So now here you can actually look at the Z transform table. I think we have something like that in our table. Okay. So if you look at the table, so we do have something over here, right? So this is basically the same format. When A equal to 1, that's what this is, right? Yeah. You could also do a partial fraction expansion and you look at the table again, but you save yourself a little bit trouble here. Okay. Okay. So look at the table. You will be able to obtain this Z transform, which turned out to be this expression in here. Okay, this expression. And the 1 minus Z to the power negative 1. And this guy here, okay, this is equal to Z minus 1 over Z. Okay, so this one here. Yeah. So you can see if you use this one, multiply this one, you actually will cancel this Z minus 1 here, right? Yeah. So simplify this a little bit, and you also cancel this Z here, right? You also cancel this Z. Okay. So simplify this, and you get 1 minus e to the power negative t, and then Z minus e to the power negative t. So that's basically the overall Z, g of Z here, right? This is the g of Z. Okay, so you got basically d of Z, you got g of Z, and here you have e of Z. If you plug in a fictitious sampler here, and you'll get the c of Z at here, right? So overall, the input output, you get c of Z over e of Z, which is basically the d of Z multiplied by this g of Z. Okay. So this is your basically open loop pulse transfer function for this one. Plugging all the fractions that are here, you get here's basically the final results. The open loop has a pulse transfer function, which is represented by this expression. Okay, so take an initial look at this system pulse transfer function here. Basically, if you look at the system, just like continuous system, the response of the system or the characteristic of the system are determined by the poles of this transfer function, right? Yeah. So in this case, you have a pole at 0. You have another pole at here. Okay, at here. Yeah. Later, we're going to learn basically. Now, if you recall, for continuous system, you have a Laplace transfer function, and if you want a stable response, and then all the poles has to be on the left side of the S plane, right? Yeah. So for a Z transform, right, or Z pulse transfer function, we also want to study the similar, basically similar principles. So that is also determined, the characteristics of the system also determined by the poles of the system. And in digital domain, essentially you need all the poles to be within the unit circle in order to have a stable response. Okay? Yeah. And it also makes sense because if you take a partial fraction expansion of each one of these into simple terms, right? And basically you see the pulse transfer function, you see this one here. Let's say if you have a term like this, and the inverse Z transform is a to the power of k, right? And a at here is what? Is a pole, okay? Yeah. So you can see now, if this is the inverse this, and you want this one to be stable, then the a value has to be within the unit circle, which is basically within either greater than -1 or less than 1, right? Yes.
With the visible system, it's really easy to understand what an unstable system is like, but with respect to digital control, like what would happen with an unstable system?
It's very much the same as a continuous system. So let's see if I have a continuous system. If I give a unit step input, for example, right? Yeah, give it to a system. And here is input. Here is output. Okay? So suppose you have a pole in the left-hand plane for continuous system. Then the typical response of the system will be basically like that. Actually more, right? So basically it's diverging, right? That's what we call unstable. That makes sense? Right? So if you have a digital system, if you give a similar unit step input here, so you'll see a similar output response, but it's instead of a continuous sketchy set here, and what you probably see is sort of like this, right? So basically the signal will explode as the time goes on. Does that make sense? Yeah? Not quite? What are you expecting?
So,
yeah.
If, for example, this was a system like filtering like an analog signal,
yeah,
because that could be a system, how would that end up being unstable if you would start sampling just values that?
It's yeah. See, we're actually thinking different perspective, right? Yeah. As just a filter, that's a stable one. That's fine, right? Yeah. You're not really making the system unstable. Okay. So let's say you put a first order filter, low pass filter here. You're not gonna make the signal unstable. Whatever the signal's into it, you're just filtering out the noise there, right? Yeah. But controller is, when you design a digital controller, it's not just as simple as just like you have a first order or second order low pass or high pass filter. You know what I'm saying, right? It's a more sophisticated filter actually. So it takes manipulation of the signal, and you're trying to generate a different signal, which is a control signal, right? Yeah. And then you control the system. So it's a lot more sophisticated than just a filter design, right? And then because of that action, and you could cause the system basically becomes unstable output essentially. Yeah. Okay. Yeah. So, for example, if you look at this one here, right? Here is basically the transfer function at here. Okay. So there are two poles, and this is a stable pole. Now, if you look at this one and here, for this value, really, when you look at the exponential function, it really doesn't matter what this sampling time t is. It's always greater than 0, right? And it's also always what? Because it's negative at here, it's always less than 1. Okay? Yeah. However, okay, so basically if you look at this, okay, so both poles are within unit cell, so you're gonna have a basically stable response for the system here. Okay? Yeah. But as t, if you let's look at the sampling time, if you pick the t becomes smaller and smaller. Okay? So if t approach to a very small value, then what does this e to the power negative t approach to now? It'll approach to 1, right? So 1, it's not going to be exactly 1, but it will be very close to 1, and then 1 essentially it's somewhere close to the edge of the unit circle, right? Yeah. So if you look at the Z transform table, when you have a value a that is close to 1, or maybe just 1, right? Think about just 1 here, or even just not negative 1, just 1 here. Then you have a response-wise, you have a constant basically, right? Instead of reducing, you have a constant 1 there. That makes sense, right? Of course, if a is greater than 1, then you have a constantly increasing value, right? Yeah. So as t close to 0, so the system response will tends to, not like t is 1 or bigger value than 0. It's much more stable. So as this responsive system will tends to become less stable, but it's still stable. Okay. Yeah.
So as this becomes a continuous system, it goes less stable.
Yeah, but it's still stable, right? So, for example, for continuous system, what's the critical? It's basically you have a vibration that's constrained like that, right? Yeah, that's still stable, but it's critical condition, right? Yeah. So that's the nature for this simple system in here, right? And the other observation is you have a constant value here on the numerator, right? So if you look at the numerator is 1 minus e to the power negative t. So similarly, let's say if a t approach to 0 and that approach to 1, then this value here will approach to what? 0. So approach to 0, this guy here, essentially this is a sort of like a gain. Okay? This is like a gain here, right? So whatever the value, input value here, ultimately will be multiplied with this one here. Okay. So if that goes to 0, then you would expect, as t go to 0, then you expect the response of the system will become very small, right? So that's observations based on this simple pulse transfer function. Okay. Yeah. Now we can. I'm not going to go into detail now. So we can basically do some simulation to check out the system response. Simulation basically means you can insert any type of input to the system. So for example, given a unit step input, and unit step input, if you look at the Z transform table, here's the unit step input, and that corresponding Z transform is Z over Z minus 1, right? So that basically means your input E of Z is Z over Z minus 1. So here your input is a unit step input, and C is output at here. So I can use, now I can see, okay, so then my output C of Z, okay, is equal to this original pulse transfer function. This is original pulse transfer function at here. Was it original like that? Yeah. There's also Z at here, right? And then times this E of Z, okay, like this, right? So this is your output C here, and you get 1Z cancel out. Then your C of Z output is this divided by this and that, right? Yeah. And that's it. That's basically the system at here, right? The system output. And you have basically 2 poles at here. Then you can do a partial fraction expansion. I'll skip some of the steps at here now. Okay, yeah. So now let's see, what we want is, what is this output C of k at here, right? What's the output C of k? So now you basically wanted to do an inverse Z transform for the C of Z, right? Yeah. And we learned in the previous lecture, in order to get the inverse Z transform, first step, divided by Z first. Okay. So divided by Z, and so let's just write a few more steps at here. Then give Z minus 1, and Z minus this. Okay. So you get this one here. Then you do a partial fraction. So now you have 1, 2, 3 poles. So you should do a partial fraction expansion as A over Z plus B over Z minus 1, and then C over this e to the power negative t, right? The partial fraction expansion. And then use the formula to find the residuals value A, B, C. Okay, and you can find the A is equal to 1 minus e to the power negative t, and then B equal to 1, and then C equal to e to the power negative t minus 2. So now multiply the Z back to the right side and use the table to find C of k, right? So that's the whole process as to finding the response. Okay. So I want you to try it. Okay, so you can find the C of k now. It's given in the lecture notes. Okay, yeah. So and then I'll just show you. You can also use MATLAB to help you do the simulation. Basically, so basically, this is the command I think I showed you, if you recall that when we were trying to simulate just the C of k or Y of k, any kind of a pulse transfer function. You give an input as unit step input. Okay, so this portion in here is unit step input. So only the 100 steps, all of them are 1, right? And use the command filter. Okay, and the system is numerator, denominator, which is the C of k, right? So you can get this is a response. Okay, so you have a basically a response like that. Okay, yeah, that makes sense. Yeah, I think I give a different options here. Instead of using filter, you can also try the command step Z. Okay, so that should give you the same type of response in response results here. Okay. You can also try impulse response. Impulse response basically means the E of Z, instead of a unit step, it's a unit. It's a Kronecker delta input. So basically, your E of Z will be just 1, right? So when n is equal to 1, it will be just 1. Okay, yeah. And then you can also look at the response when you have a impulse response. Okay, yeah. So try out this thing here. Okay, and this is basically you can use any of the command here to help you with your assignments, right? Yeah, just very little bit of verification. You're going to simulate a different system, right? Yeah. Okay, so that is all about basically open loop pulse transfer function. Right? Any questions? Good. So there's one basically concept we need to finish before we move on to the closed loop pulse transfer function. Here the concept is called concept of DC gain. Okay. This is a very important control concept in the stability for a control system. Okay. So what the DC gain basically means, okay, the definition for DC gain here is, okay, so basically you're looking at what is the steady state gain, okay, for a constant input. So what's the steady state gain for constant input? So like the question was just asked, when you see unstable system or stable system, right? Yeah. If you have a stable system, basically means the system will always settle down, right? Will always settle down to a certain value when your input is a constant input. Okay, so that's basically what stable means essentially. And if your input is a unit step input, and then your output, let's say, maybe with some variations, okay, and or oscillations, it'll settle down. Here is your steady state value here, right? I don't know what this value is, but then you use this value divided by the 1. That basically is the so-called steady, the so-called DC gain here. Okay, that's DC gain. So as you can see, so basically the DC gain at here is equal to the SS over 1, or just equal to the SS value in this case, right? Yeah. And the same concept applied to both the continuous system and the digital system. Okay. Yeah. So let me ask you a simple question at here. Let's see if you want to have a precision control system. What do you want the DC gain to be? That's right, it's 1, right? Yeah, precision control system basically means you want your system to follow the input, right? So you want the steady state value to be 1. Okay, other than that, you don't want it. So then you want the DC gain to be 1. So in other words, the DC gain equal to 1 basically means the steady state error equal to 0, right? Yeah, exactly. Okay, so this is typically what you struggle or what you're trying to achieve when you design a control system. You want a DC gain to be 1. Okay. 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 So then I'm gonna basically look at what the DC gain is for discrete system here, but we should look at the continuous system too. Okay. So for continuous, just for comparison, for continuous system, when you have a unit step input, which is represented by 1 over S, and then the plant at here, okay, So the DC gain, okay, is equal to this one here. And this is your formula for DC gain. Okay. Now if you look at this one here, this is actually not a new formula. This one here basically is, if you recall that, this essentially is what? The final value theorem, right? The final value theorem. So here's your plant, and then times the input, okay? And then you ask, what's the final value for this one? How do we find it out? And here's the final value theorem. Just times S, and then that S equal to 0, and you'll find the final value. So in this case here, cancel the S first, and that basically what you're calculating is, if you have the plant head here, just let all the S equal to 0, and then you can get the DC gain, right? For discrete system, okay, for discrete system, what we do is basically let's say this is a sort of a discrete system. Now, I'm simplifying the system here. So this block right here could be a zero order hold, and then in series with a plant, right? So this simple block could be these two together, right? Yeah, could be these two together, or it could be a results. It could be a results of a closed loop pulse transfer function. Okay, yeah. So either way, you know, let's say you have input here, and then you have output at here. Okay, so the DC gain in this case, okay, you're talking about what is the steady state value for the output, right? What is steady state value for the output at infinite, right? Steady state. And then you're looking at essentially discrete one here. So first find this C of Z. Okay, first find the C of Z, and of course that corresponding to the unit step input, Z over Z minus 1, right? So we need to find what the C of Z is, and then and use the final value theorem, right? Final value theorem, and this is a discrete version, final value theorem. Okay. And in this case, your C of Z, of course, is basically the input times the output. So input is this, and then input times the plant at here. Okay. So now this plant, of course, will have to be converted to the Z transfer function first. Okay. So that's your DC gain for the discrete system. So whatever the G of Z, and then you'll plug it over here, right? And then there will be a few things that will cancel out. This is Z minus 1 over Z, so all you're left with just G of Z now, or just G of 1. Okay, yeah, just G of 1. So now you see that for the discrete system, the DC gain is to replace the Z with 1 for this, which is represented this block right here. Okay. And then you get your G, then you get your DC gain here. Okay, the DC gain. Good. Yeah. So you can try the calculation of DC gain for this example here. Okay, for this example, so this is example here, right? This example. You can try the DC gain. Basically, see this is your C of Z. Here's your C of Z. Then what happens when you substitute Z equal to 1, right? And what do we get? So if we sorry. Yeah, that's right. So we have here. So you have this one here, right? You have try this formula here, right? So this 1 minus Z to the power negative 1, and then times the C of Z, right? And C of Z is this portion here. Okay, is this portion. Now you do have a z minus 1 here, but that will cancel out with the z minus 1 over here, right? Yeah. So if you substitute z equal to 1, okay, and you again up with just a 1. And as a simulation, you see here, the simulation here, it's 1, right? Yeah. Okay. So that conforms with the your expectation. Is that okay? That's for DC gain concept. Okay, very good. Okay, so now let's look at the next next topic, which is the closed loop pulse transfer function. Okay, closed loop pulse transfer function. And this is more typical because when you design control system, and inevitably you most of the time, okay, you design as a closed loop system, and it's always a negative feedback closed loop system, right? Yeah. So I'll approach this using a few examples, okay, to derive the closed loop pulse transfer function. Okay. Here's the first example, or the first type of closed loop. Okay. And this is a very simple system. Basically, you have two blocks. Typically, the h of s that are here could be representation of the sensor. Okay, and then this one here could be maybe a 0 to hold plus a plant. Okay, yeah. So if the input is, let's say, a reference input at here, and the output is y of s. So what we're interested in is what is the pulse transfer function. Right. So that's the idea. Yeah. So to derive pulse transfer function, okay, so I'll give you two different ways here. If you think back the open loop system, how we did it, right? What we did is basically we follow the signals, we follow the flow of the signals basically through all the blocks from the beginning till the end, right? Yeah. And then we try to find basically the y star of s over over the basically output star over the input star, and then you convert s into the z, and then you get the pulse transfer function, right? Yeah. So we can do the same thing. We'll try to do the basically in the same approach here. We'll follow the flow of the signals here. Typically, this is basically representing is the error here, right? So the reference minus the feedback. So this minus negative feedback is the error. Then you have an impulse sampler at here. So anything after the impulse sampler is represented using the star, right? The E star of S. Okay. So that's as much as for now, you know, basically the signal you can label it here. So now let's look at the output and also look at the error message, at the error signal at here. For the error E of S, okay, that equal to your input, reference input, and minus this signal at this location. Okay? And the signal at this location, the question mark, okay, is equal to what? The output multiplied by the h of s, right? So that equal to the h of s and multiplied by y of s. So let's call this is equation 1. Okay. At the same time, your output y of s is equal to the input to the block g of s, which is E star of s, times g of s. And let's call this equation number 2. Okay. So now I can substitute equation number 2 into equation number 1 for the y of s. Okay, so you're basically sub 2 into 1. We get our e of s, okay, equal to r of s minus h of s, g of s, then times e star of s. Okay. And let's call this is equation number 3. Okay. Equation number 3 here. Good. So from equation number 3 and equation 2, so these two basically is what we need to focus on at here now. Okay. Yeah. For equation, first let's look at the equation 3. So you take star Laplace transform. Okay, so take star Laplace transform, that's operation, right? So take this operation for both sides of equation 3. Okay, for both sides of equation 3. So then what happens? The left side here, that's simple. That just become the E star, right? So they just become E star here. And then for the right side here, okay, the star Laplace operation is linear. So you have R star here now, okay? And then the second term here, okay, the second term here is what? Is H of S, G of S, and E star of S star, right? Yeah. Okay. And what does the second term give you? So what's the star Laplace transform or operation for the whole chunk inside this bracket? What does this one give you? Does that give you? Exactly, right? So remember, it's not H star, G star, E star. Okay? Yeah, that's the K4 there. So this should be G. Multiply these two together first, and then apply the star. Okay. Yeah. Good. Yeah. So now from here, you can have a expression for E star now, right? So you could have an expression for E star. Just move this term to the right side, to the left side, and then divide both sides the coefficient. So you get R star of S over 1 plus GH star of S. Okay. That's E star, right? E star. Okay. Okay. So let's go back to this equation number 2, right? Go back to the equation number 2 here. So for equation 2, okay, and we do the same thing. We take the star operation, star Laplace operation, this one here, take the star Laplace transform for both sides of equation 2, right? So that gives us what? So that gives us Y star, of course, one side, and the other side is E star already, so E star G star, right? Okay. That makes sense? So now I have derived the E star already. This is the E star. So let's say this is equation 4. So I'll substitute equation 4 over here. So that gives me R star at here, G star at here, and then divided by 1 plus GH star at here. Okay. Remember what we're looking for? We're looking for the ratio between Y star and R star, right? The output and the input. So now we have the ratio now. We have the Y star at here, and we have the R star at here. And overall the ratio is, okay, this one. So if you look at the final results, it's consistently star Laplace transform everywhere. Okay? There's no mixture of regular S function or star. It's all star one, right? It's all star. If it is all star, then we basically will say, okay, let's just replace the S with the 1 over capital T ln Z. Then we get what? Our y of Z over R of Z equal to G of Z and GH of Z. Okay? So this is basically the closed loop pulse transfer function for this simple closed data sample closed loop system. Right, so this closed loop system here has a pulse transfer function which is this. Okay? Yeah. Of course, if you know what the G is, what the H is, and then you can figure out each one of this, and then you can figure out the whole expression. Right? Okay. So, but I do want to make a comment here. And before we look at another example here, okay? I'll use PTF for the pulse transfer function. Okay. Now, pulse transfer function, okay, doesn't necessarily exist, okay, for all closed loop system. So what does that mean? Basically, is this is where we're trying to find a ratio between the y of z and r of z, right? Yeah. But for some closed loop system, for data sample closed loop system, you don't necessarily are able to derive this ratio here. So for example, right, you can try yourself. If this is a closed loop system, so for example, if this is a closed system we're looking at here, okay, and I want you to try it. To try basically the same approach that we did, you know, you label E of S, label this star thing here, and then here's your Y of S at here, okay. See if you can find explicitly, basically this is what I mean, explicit, right? An expression representing, you know, describing this ratio at here, or maybe just say here, right, describing the y star over r star. Okay, see for this one if you could do that, and then of course the answer is actually yes. It is no. So in this case here, this one doesn't exist. Okay, so you can try it. You'll be able to find actually an expression for y star, but then that expression doesn't explicitly have the r star showing, so basically you can't find a ratio. Okay, yeah. Now, why this one doesn't exist? Yes.
In that example, are you adding a discrete signal to a new signal or subtracting it?
Which one here?
So after it's sampled, and then
yeah, this is basically continuous minus continuous, right? Here is a continuous here.
Okay.
Yeah.
Is that the reason why?
Excellent. Yes, that is the reason. Yeah. So this is actually my second comment set here, right? Very good. So the second comment here, there needs to be an impulse sampler, okay, right after the subtraction junction. Okay. If you want to have this impulse transfer function for a closed loop, you have to have an impulse sampler right after this subtraction junction at here. Okay, yeah. So that's the necessary condition. So essentially, for example, if that's what I mean in here. So that's the impulse sampler here, okay? And then maybe it's a zero order hold, and maybe it's you have a plant one like this, and then you close the loop, right? Yeah. So if you think about that, you know, we did an exercise like this is a simple open loop. We did it, right? And then you can close the loop like this. But you do need this one here in order to have that impulse transfer function. Okay. Yeah. Okay. So well, maybe we can try this here, right? We can try this. I think if you recall that this one here we did it in the previous example. This one here we got our g of z, which for open loop we got this, right? We got this. Okay. In previous example we got this one here. Now for this system in here, if you're required to derive the you're required to derive the pulse transfer function for this system in here. So apparently you will get, okay, essentially g of z over 1 plus what should be here? Relate to the first example. So if you look at the first example here, here's a g, here's h, right? That g essentially is a combination of these two at here, okay? And then in this case you don't have any h at here, so the bottom here should be g of z, okay? G of z. And g of z is given, right? So you derived already for the open loop, and just plug it in, and you get your closed loop, which turned out to be there's this stuff. Okay. Good? Yeah. And you can always, by looking at this, this is basically your closed loop relating the input and output at here, right? Pulse transfer function. And then you can literally just do an initial analysis by looking at this PTF, and then say, okay, what's the pole? What's the pole here? The pole is what? -1 plus this guy, right? That's the pole here. Okay. And for this pole at here, okay, and then you probably say, okay, if you don't know, then if you don't know where this pole is, right, and but you do know is what I really want is I want this pole to be within a unit circle. So which means I want this this pole, right, the absolute value of this pole to be less than 1. That makes sense, right? So then we can try to solve this one here. Say, okay, that means this will be greater than -1 and less than 1, right? And then that simplification end up with a 0 here, and then here, and then like this. Okay, and this is a naturally satisfied condition, right? Yeah, this is naturally satisfied. So it doesn't matter what the sampling time t. This is a naturally satisfied condition. So which means your pole at here is a good. It's a stable one there, right? Yeah. Okay. So and that's a comment, you know, basically, right? Another comments here. So this is the first comment. This is the second comment here. Okay. And so one more comments. Okay, one more comments. As you can see, okay, like this in this example here, you know, t is sampling time, and t is related to sampling frequency, right? Yeah. Okay. Yeah. So apparently, your choice of sampling frequency will affect the pole's location, right? Yeah. And that essentially is the third comment here. What would be a proper choice or proper value of this sampling frequency omega s? Okay. Yeah. I'm not sure if you recall I don't remember which lecture now. You know, there is a fundamental theory that actually put a constraint on this sampling frequency omega s, right? It's sampling the Shannon theory. So that's basically saying the sampling frequency has to be at least twice as much as the bandwidth of your system. Okay? Yeah. But that doesn't mean that you have to choose that twice as much of the bandwidth of system. Okay? Yeah. So of course, basically this is your first constraint here. So the choice of this one here, you have to depends on the omega b, basically the bandwidth of the system. Okay, it has to have the constraint here. Typically, okay, you could take is between 5 to 10 times this omega b, the system bandwidth. Okay, so you want it to be basically faster enough sampling there. Okay, yeah. So that's typical choice you could use, right? Yeah. So let's see, for example, if you have a system, right, very simple system. Here is the first order system here, right? Here's first order system. And for this particular system, and you have a tau times s plus 1. And if you recall in your continuous system, this tau here is called the time constant. Okay? And time constant basically means how much time it takes for the system to reach, for the system output to reach 63% of the steady state value, right? That's time constant. So if you have a system, if you have a, let's say, a temperature sensor, right, and you measure temperature, and you look at the basically reading of this sensor, so you put in the hot water, and then you can plot out, and that plot out is basically first order response, right? Yeah, it takes some while until it settles down at the temperature of the water, right? Yeah. So that basically gives you first order response, and then the tau, this is the first order system, right, representing the first order response. So the tau is the time constant. How long does it take to reach 63% of that steady state value here? Okay. Yeah. And when you plot this, when you plot the body plot, it typically for first order it looks like this one here, right? Yeah. It's basically a low pass filter, and then you have essentially over here. This is your bandwidth, and this guy here representing basically a negative 3 dB drop. Okay, so here's a flat and start to drop, and then at this location it's negative 3 dB drop, and then further from that location you have more drops. Essentially, if you go further from here, then anything output will be too small, right, to mean anything. So your bandwidth basically for this system is just 1 over tau, right? If tau equal to 1 second, then your omega b, right, will be just 1 reading per second, right? So that's your bandwidth. So if I use this guideline here, then my omega s for sampling time, my omega s, let's if I choose 6 omega b, so that'll be 6 reading per second. Okay, yeah. So that's the kind of example here, right? Yeah. For sampling, choice of sampling frequency. But this is not everything that this guideline here, just a guideline here, right? Yeah. Sampling frequency, you should also consider. So another thing is you should also consider the sensor bandwidth. Okay. Yeah. So some sensor maybe have a very quick response, but some sensor are just designed to be a sluggish sensor, especially like some temperature sensors, work in wood processing. Okay. So the sensor may be, let's say, for example, 20 milliseconds. So basically means the sensor maximum response is 20 milliseconds, right? So what does that mean? That means you don't really need to pick a sampling time faster than that, right? Because there's no meaning to be faster than that. Okay, yeah, you get the same basically reading as you're picking within the 20 seconds. There's also a consideration for CPUs, your processor, right? If you're using an Adreno, there is certain working frequency. If you're using a Pentium computer, you have another frequency, right? Yeah. And for digital control, basically, for example, if this is your sampling time t, okay, so you're essentially you want your computation to finish within this time period, right? Yeah. And Arduino controller, the fastest computation time is not comparable to a Pentium. So which one can fit? If you have a very sophisticated controller or sophisticated program, it takes maybe a long time to run, right? So then your choice of a CPU will also limit your sampling time over there. Okay. Yeah. So that's the third comment. Okay. Any questions? Good. Yeah. Okay. So let's look at another example at here. Okay. Let's look at one more example, and then we're just trying to observe. Here we're trying to observe a difference. Alright, so look at this particular example. First, maybe try to observe what is the difference now, okay, and compared to the first example. Here's a closed loop system, negative feedback. Okay. So what's the difference compared to the edge example? Let's say I'll still call it this is y of s. I'll put it here, but maybe this is y of s is equal to a signal m star of s, for example. Okay, yeah. So I guess you notice now the difference here. You have an extra impulse sampler here, right, compared to the previous example. Okay, yeah. Okay, so now what will be the impact of the effect of this extra impulse sampler to the closed loop system? Okay, yeah. So let's try to follow through the same method, okay, as we did in the previous example. First, label the signals, right? Label the signals before and behind the impulse sampler. And for the closed loop system, you always work around this junction at here, and also work around the output. So E of s equal to R of s minus this H of s, right? And then time Y of s, okay? And Y of s. And in this case, your Y of s is the same as M star of s in terms of the labeling of the signals. Okay. And then let's look at the output here, right? Look at the output. Now, before looking at an output here, so since Y of s is same as M star of s, so your M star of s, what does M star of s equal to, right? Yeah. Maybe start with not M star, maybe just start with M of s, right? Start M of s. So M of s equal to G of s times E star of s. Okay. G of s, E star of s. And now we see, okay, so I'll skip myself this. So I will take star operation. Okay, let's take start operation here. So that gives me M star equal to G star times E star. Okay. And then I'll do the same thing. I'll take a star operation for this first expression here. So take star here and here. Good? Yeah. Before I take the star, I'm going to replace the y with m star first. So basically this guy here, replace that with m star. So then here I got E star on one side, here R star. So this guy here, remember I replaced this with m star here. Okay, so it's y equal to m star, right? So that equal to h star of s, and then times m star of s. Okay. Good. So m star we derived, which is this one here. Okay. So we can substitute into that expression. So that gives us r star of s minus h star of s, then g star of s, and e star of s. So now derive an expression for E star. So you get R star of S at here, and divided plus G star, H star, like that. Okay. I think by now, and you should probably realize the difference now, right? And if you look at the denominator, the previous one is what? It's a GH star, right? Here is a G star, H star. So, of course, we're looking for is Y star over R star. And then the output is Y star equal to G star, okay, times E star. Okay. So, probably I should write more one step here. So Y star equal to M star and equal to G star, E star. Okay, so combine these together, you get Y star of S over R star of S, and that equal to G star over 1 plus G star of S and H star of S. Everything is star, right? Consistent. Everything star. And then you can replace S with 1 over T and then turn everything into a Z.
Replace S with 1.
Yeah, S.
T log.
That's right. Yeah. Yeah. Okay, so you got your Pulse transformation. Okay, but I want to also caution you at here. The way I'm doing here is I'm trying to derive to show you what the Pulse transformation, closed loop Pulse transformation is, right? Yeah. Of course, if you have the actual block information G of S, H of S, okay, and you're required to derive to this guy here, then you don't need to. You actually don't need to. You can, still you can, but you actually don't need to get the G star, H star first, and then you do the replacement. You can actually do what? You just find what the G of Z is, right? Corresponding to G of S. And what the H of Z is, corresponding to H of S. And then you plug it in here, you get your closed loop Pulse transformation. Okay? Yeah. I mean, not that you cannot do this, right? You can start from here, find a G star, and then replace this, but it's a little redundant. Okay, yeah. So that is all about the closed loop Pulse transfer function. Okay, yeah. Now, if you observe this one here, the difference is that originally the previous one is the GH is combined, right? And here the GH are separated now, okay, into G of Z, H of Z. And because the two blocks in between now have a what? Has an impulse sampler here, right? Has an impulse sampler. So this existence of the impulse sampler basically for any block, okay, if you want to write that block into a single, let's say g of z, then that block has to be basically separated by an impulse sampler. Okay? So that gives us actually a tape here. I'll give you a tape in terms of a different way of deriving this alternative method. Let's call it alternative method of deriving, okay, closed loop PTF. Okay, yeah. So here is the steps involved. Okay, step 1. Okay, derive the continuous transfer function. Okay, derive the continuous transfer function. So here's a closed loop. For example, this is a closed loop here, right? Derive continuous basically means pretend that there's no impulse sampler. Just close this switch, close the switch, and to treat it as if it's a continuous system. Is okay, right? Yeah, that's basically what this step means. Okay, and then step number 2. Okay, so basically now step number 2, you observe, you go back to the discrete one, right? Go back to discrete one, and then you observe it. So then you look at it. So let's say, ask yourself, if there is a impulse sampler, okay, if there is an impulse sampler separating the S block, okay, separating the S block, then all you need to do is you change the S function. So you say first step, you derive a continuous transfer function, which involves possibly the G, the H, or whatever, any other blocks, right? Yeah. So if there is an impulse sampler separating that particular S block, then you can just change the S function to a Z function. Okay. Yeah. So I'll show you an example. Okay. Now this is the first if, right? So what if not? So if there is, if not, okay. So basically, if this block is not separated by impulse sampler, then what do? Then you basically you move around this block. Okay, move along the block, combining. Okay. Combining the S blocks. So keep going, right? So if there's any blocks after it, combine it with the next blocks. Combining basically means you multiply this block, the S function, with the next S function, right? Until the next sampler. Okay, until the next sampler. Okay, good. So then you have this impulse sampler until the next sampler, and then followed by another impulse sampler. So now you put these two, all combine them together. So I'll show you an example here. Okay. Oh. So let's see, here is a simple closed loop system, and we want to derive the pulse transfer function. Okay. So I would encourage you to try out the approach that we just did by going through the flow of the signals here, right? So let's say you have an E, you have an E star, you have an M and an M star, right? Like this kind of approach, okay? Yeah. And try see what happens here. Now, if I use the table that I give it to you right now, first step, derive the closed loop trans function, continuous system. So close this switch, close that switch, and what's the closed loop transfer function, right? Yeah. If you don't know, then you should review what you learned in 315. But there's quick part is it's always so if this is a block here, and then you have another block over here, over this branch right here. So the top one, the numerator, it's basically the numerator is a combination of all the blocks in this branch, right? And in this case, just H, right? Yeah. And then 1 plus what? 1 plus everything in the feedback branch, then times this forward branch. Okay. So that basically is 1 plus G1, G2, and H. Is that good? Right? So if you have a closed loop system, continuous one, what's the transfer function? Just remember, you do have actually a shortcut, right? Yeah, a trick. Now, once you get this, now open up the switch, and let's follow the second steps here, right? So, for example, there's H of S here, okay? H of S. So this H of S is a standalone here, right? So it's not associated with anything else. So that basically you can change that to H of Z because this is on the numerator. It's a standalone here. Okay. Yeah. And then the second one here, the denominator here, you have a G1, G2, H. So that's where you got to be careful now. So can I just simply change the G1 to G of Z? Can I simply change the G2 to G of Z? Can I simply change this H of S to H of Z? So that's the question you have to ask this two ifs at here. So for example, G1 of S, where is this? It's here, right? It's here. So G1 of S, is this separated by impulse sampler for this block? No, right? So you can't just change this to G1 of Z. What about G2 of S? There's one here, and there's one here. So that's fine, right? So this one is G2 of Z at here. Okay. Okay. So what about G1? You see, with G1, we can't change that to G1 of Z. So we remember, and then also H. If you look at H here, because H is not like this H. This is at this location, right? So H, before, after, there's only one, but then not after, right? So you keep following, combining these two blocks together, so that these two blocks are separated by the two impulse sampler here. So that you combine these two here, becomes becomes G2H of not S, Z. G1, yes.
And with that, you basically just multiply the S over here.
That's right.
And then
convert to the Z. Yeah. Is that clear? Yeah. So in an exam setting, okay, which I typically will test you one of such an example in the midterm, watch carefully what the question is actually asking for. If the question is just asking is derive the pulse transfer function for the closed loop system, so it doesn't restrict you anything, right? So you can use any method you want to derive. That's fine, okay? If the question asks you to use the star Laplace operation to derive, then you use what? You use this method here. Is that clear? Yeah. Okay. So, and of course, there's nothing wrong if you get the right result. You should get the same results, right? Yeah. In my opinion, this is much simpler. Okay. But this one here, it's a reflection of actually a concept what we're learning, right, in this class. Okay. Yeah. Okay. Good. So this is all about closed loop pulse transfer function, okay? And yeah, it's always a little awkward to give you 5 minutes here. Could talk about the 5 more minutes. And next topic, okay? I think I'll leave it to next lecture. is about discrete equivalence. Okay, so basically, if I have a, how do I basically come up with a digital controller, right? What are the two possible approaches we can use to come up with a digital controller? And one approach is the so-called discrete equivalent, using numerical methods to equivalence an existing continuous controller to a Z block. Okay, so we'll talk about next lecture. Any questions? Okay, all good? Thanks.